Venus, our nearest planetary neighbor and our sister planet. Comparable in size to the Earth but approximately 40 million kilometers nearer in orbit to the Sun, the second planet of our solar system has been a source of tales, myths, and legends for ages. More recently, though, we have moved beyond being able to merely see that shining disk near the Sun at the beginning and end of each day. Starting at the peak of the Cold War, several robot missions have been dispatched to Venus to view, orbit, and in a few instances, even touchdown, and with technology able to see not just the visible light but also the infrared, ultraviolet, and radio spectra, what we have discovered is a world that is other to Earth in nearly every conceivable way. Come with us today on this supercut as we make a journey to the star of morning and evening, employing technology both ancient and modern to reveal the secrets of Venus, and coming down through its dense atmosphere to reach the surface of our nearest neighbor. What you should know about Venus is the second planet from the Sun, and it's our nearest neighbor. Its mean orbital distance from the Sun is 0.72 AU, or approximately 108 million kilometers. It doesn't deviate much at all from this mean orbital radius, since it's the planet with the most non-eccentric orbit, traveling in a practically perfect circle. At Venus's point nearest to us, it is the nearest of any other planet, at only 41 million kilometers. Oddly enough, though, this isn't when it's brightest in our sky, since when it's nearest to us, we only notice the night side because it's between us and the Sun. It can still be seen. However, as the sunlight bends through the atmosphere, it's really brightest when it's a thinner crescent shape in the sky, and when this occurs, it is the brightest object we notice at night aside from the Moon. Consequently, Venus is habitually misreported as an unidentified flying object. U.S. President Jimmy Carter claimed to have seen a UFO in 1969, which subsequent analysis indicated was likely Venus. Thousands of other individuals have confused Venus for something more exotic because of its eye-popping brightness. I recently had the opportunity to gaze at Venus with a telescope, and incredibly, the crescent form of it was very apparent. Since Venus is in between us and the Sun, it might cause you to wonder if Venus ever eclipses the Sun from our perspective on Earth. And the answer is yes, but surprisingly, very infrequently. Transits occur in pairs, the pairs being 8 years apart, but each pair occurs only once every 100 or some years. The last transit we experienced was in 2012, but unless you saw that, I fear the next one will not be until 2117. The reason for this rarity is due to the fact that Venus's is not exactly the same as Earth's. Also, Venus only catches up with Earth every 584 or so days. These two things combined ensure that, although a spectacular and predictable sight, it also means we'll probably only ever have the chance to see it once or twice in our lifetimes. All the planets revolve anti-clockwise around the Sun, and with that, Venus is not an exception. But in contrast to all the other planets, it rotates in a clockwise direction, or rather in a retrograde rotation. Not only that, but it rotates very slowly, revolving once every 243 Earth days slower than any other world. This results in a sidereal day longer than a Venusian year itself taking 224 Earth days. A sidereal day, in case you recall from my Mercury installment, which you can read here, in case you missed it, is one revolution of the world. Due to this retrograde rotation, however, a solar day, sunrise to sunrise, is significantly shorter, 117 Earth days. Which is to say you'd only get to experience less than 2 days in a year in Venus. To put some perspective on how glacially it turns, at the equator it's only moving at 6.5 km. Its slow spin makes it the second most spherical body in the solar system, except for the Sun. It is not known why Venus spins in the opposite direction to the other planets, but it may have been caused by a massive collision with another body billions of years ago, or tidal locking to the Sun, or tidal forces on the Venusian atmosphere. Up to now, all of these are things that we can study through long-range observations, made right here on Earth. But for a lot of years, that was all we had to base it on. Like a coy and teasing lover, the planet Venus wraps itself in a literal veil of mystery, a dense enveloping cloud that conceals its secrets, and persuading Venus to give up those secrets would be no easy task, as the earliest scientists who attempted to charm her discovered to their dismay. I do find it ironic that on a planet so named for the goddess of love, Venus is amongst the most dangerous and inhospitable planets conceivable. That just doesn't feel right. Or does it? Let's see what those early attempts at unlocking Venus's hidden face showed them. What did they discover? And what do we discover on the real face of Venus? Why Venera went silent on Venus, being the second brightest object in the nighttime sky and also the nearest except the moon in distance at times. Venus has ever drawn a crowd of those who would look up into the heavens. Yet even in today's age, travel between planets is difficult. And during the peak of the Cold War, it was even more difficult. Of the initial 15 missions that were flown to study Venus from 1961 through 1967, only 3 were successes as far as accomplishing their particular goals, Mariners 2 and 5 by NASA, and Venera 4 by the Soviet NPO Lavochkin. Successful atmospheric entries with Venera 4, 5 and 6 soon followed, and in late 1970, the USSR finally passed a massive milestone with Venera 7, the first space probe to land on the surface of another world and last long enough to send back information about it. Come along with me as we track Venera into those perilous, obscuring clouds to discover what is beneath. Still floating around in space, Venera makes its way towards Venus. As it descends onto the planet, Venus's upper atmosphere stretches out before it. From the edges of space at about 250 kilometers above the surface, and down to about 60 kilometers above it. Here, it finds nothing but a thin haze. 99% of Venus's atmosphere by mass exists below this point. This means that Venera's fall through this layer is simple enough, in very much the same manner as our own atmosphere would be at similar altitudes. But Venus's upper atmosphere's chemical composition could not be more different, a sign of things to come as we and Venera descend further. Rather than a majority of nitrogen and oxygen as on Earth, we start to pick up traces of carbon dioxide. It's not enough to cause significant effects on the temperature at this altitude, but it's significant as a marker of what lies beneath. Other than the difference in chemistry, however, at this altitude, the atmosphere behaves roughly the same as that of our home planet at similar altitudes with vast temperature differences between day and night. Highs of 37 BC to lows of 143 BC. For Venera, this is the easy part. An interesting sideshow to the noticeable presence of carbon dioxide is the presence of some oxygen atoms, which emit infrared radiation that can be seen by telescopes and spacecraft. Here, in this image captured by the Venus Express orbiter at infrared wavelength, the blue is the air glow due to the oxygen high up in the Venusian atmosphere. As Venera descends through the layers, it reaches the main visible cloud deck of Venus, at about 60 kilometers above the surface. The dense, dull yellow we see in images of visible light is nearly all due to this cloud deck, ending roughly 40 kilometers above the ground. In this region of the atmosphere, ultraviolet radiation from the sun dissociates carbon dioxide to carbon monoxide and isolated oxygen atoms. These react readily with sulfur dioxide and water vapor, 2 other trace substances in the atmosphere of Venus, to create the clouds of sulfuric acid that we observe. Sulfuric acid, incidentally, is extremely corrosive, and the acid rain created just adds to the hellishness of Venus, though it does evaporate on the way down. But that is still to come. You can see as soon as you look that the surface of Venus cannot be observed through the thick cloud cover of the planet, so Venera will have to proceed in blind. That same cover bounces about 3/4 of the sunlight that strikes Venus, sometimes allowing as few as 10% of sunlight to pass through, as the ice crystals formed from the sulfuric acid that floats in the atmosphere are extremely reflective. This reflectivity goes a long way towards explaining how bright Venus looks, both to satellites going by and to observers on Earth. Remember, it's the second brightest object in the night sky. These clouds are also capable of producing lightning similar to how it is on Earth, although it's not so prevalent. When we gaze upon those mustard yellow clouds in the visible spectrum, they're dense and blinding, showing little of what's underneath. Nevertheless, we have a means that Venera didn't have: infrared sensor technology. In the infrared spectrum, things are quite different. This photo, captured by the JAXA's Akatsuki spacecraft, puts things into much sharper focus, revealing well-defined light and dark spots and bands encircling Venus's atmosphere. And here's where we can observe the dense carbon dioxide makeup of the atmosphere very clearly as well. Carbon dioxide is a good greenhouse gas. insulating the heat that comes in from the sun, leading to a wildly high surface and atmospheric temperature. Within the realm of infrared observation, this is very clear as the whole surface is glowing due to the heat produced by the thick layer of carbon dioxide. The dark stripes and patches are the clouds of sulfuric acid mentioned above, and we can observe them at high altitudes above the much brighter thick and hot carbon dioxide layer close to the surface. Can you imagine what Venera would experience as it travels through this hell? Sulfuric acid assaults its outer casing. Winds blow at 100 meters per second, 60 times the rotation speed of the planet, fast enough to circumnavigate the planet in just 4 days, which makes the planet appear to be turning much faster than it does. The temperature, which at an altitude of 50-55 kilometers ranges from 25 to 75 BRC, suddenly increases, coming to blistering levels. Venus' surface air pressure is 75 to 100 times that on Earth. Proportionately, it's like having a whole car perched on your thumbnail. And as Venera goes further down, however, even stranger conditions exist. Once Venera breaks through the underside of the sulfuric acid cloud deck, it enters clean air again. But here things are odd. The pressure here is now so immense, it's beginning to impact the carbon dioxide in the atmosphere. The carbon dioxide density at this level is so immense that it ceases to function as a gas, but instead, more as a type of supercritical fluid, a state of matter somewhere between liquid and gas in which a substance acquires some of the characteristics of each. The wind has eased down here following the confounding rapid speeds of the upper clouds. The atmosphere below is so dense that winds blow at little more than 5 km/h. It would be like wading through water with a sluggish but relentless flow, though in a river 464 BC, hot enough to reduce lead to mush. To put it into perspective, that is 34 BC higher than Mercury's highest temperature. Despite the fact that Mercury is nearer the Sun, and Venus receives only 25% of the solar radiation that Mercury does. The only difference being that Mercury doesn't possess an atmosphere to keep the heat, whereas Venus does. Which means during nighttime and even on the poles the temperature is quite stable. While most of this surface may seem foreign to us on Earth, there's one commonality: the strength of gravity. Venus's dimensions and mass are very much like our own Earth, hence the reason it's also commonly known as our sister or twin planet. Venus is one of the 4 inner terrestrial planets, and it is a rocky planet. Its diameter is very slightly smaller than Earth's at 12,100 km to Earth's 12,740 km, and its density is 5.3 g/cm3 versus our 5.5 g/cm3. This is only a tenth weaker than that on Earth.
Surface gravity 8.9 ms2. But what can contemporary technology reveal of Venus and its strata?
To better describe the immense heat at this altitude level on Venus, let's take a look at an image of the lower atmosphere of Venus snapped in the near-infrared range, a wavelength of 2.3 micrometers, by the Galileo satellite. The red, hot regions of the lower atmosphere are well visible, as are the darker spots induced by the sulfuric acid clouds higher up in the atmosphere. The lower reaches of the Venusian atmosphere are incredibly hot, and there are distinct layers of that atmosphere, different in both temperature and composition. To further demonstrate the differences between the atmospheric layers of Venus, let's now have a look at the layers we've seen so far under ultraviolet light. Although the pictures, once again taken by the JAXA spacecraft, at wavelengths of 283 and 365 nanometers do not bear much color and brightness contrast like infrared pictures, they do exhibit more variance than images observed in visible light. The regions of darkness and blotchiness of the cloud layers reveal the ultraviolet light is absorbed rather than reflected, but precisely what chemical or set of chemicals is responsible for this absorption is still a matter of debate among the astro community. Evidently, there are components and compounds of the Venusian atmosphere that continue to escape our efforts at discovery and classification. And speaking of Venus's atmosphere-resisting explanation, here's a glimpse at Venus's poles in the infrared. Notice anything strange about them? Present at both Venus' north and south poles are large polar vortexes, about the size of Europe, whipped up by those 100 ms winds. What's really weird, though, is that they have not just one central eye, but 2, and scientists are still not entirely certain why. Venus is multi-layered, Highly variable polar vortices are very difficult to model because they can vary in timescales of less than 24 hours, so they're quite a mystery. But once past the mysterious atmosphere, what did Venera observe down below? Let us finish Venera's odyssey through the dense acidic clouds and reach the surface of our closest neighbor. Earlier, we observed the very first picture ever sent from the surface of Venus. Because of the enormous clouds of sulfuric acid blocking any sort of view from space, the only pictures of Venus that reveal the surface in visible light are those that have been taken from a lander on the surface. And of those, we only have 6, taken from 4 of the Soviet Venera probes that landed, such as our Venera 7. The air is surprisingly clear. Scientists had wondered whether everything would be obscured by a thick haze, but this doesn't appear to be the case. Everything is a dull yellow, the color of the acidic composition of the atmosphere, and while we might be surprised to find solid, rocky ground under the thick, crushing air of Venus, that ground is also utterly desolate. It hints at ancient flows of lava hardened into flat plains and worn away by Venus's powerful atmosphere. All looks very parched, which is not surprising with baking temperatures. Maybe 1 billion years in the future, when the sun's luminosity has grown enough, we could see the same runaway greenhouse effects and outcomes on Earth. But here we have to leave Venera. The Venera series of probes, such as the one whose journey we have been tracing, never survived on Venus's surface for more than a couple of hours, thanks to the combination of the heat and the crushing pressure. Their pictures provide us with a fleeting but crucial look into what conditions are like down there on the rocky floor. But although intriguing, such information about the surface conditions on Venus was very far short of what researchers desired to learn. For Venera's photos could only capture a minuscule fraction of the planet's surface. But if placing landing probes on the planet's surface was proving virtually impossible, was there some other means by which one could look beyond Venus's suffocating clouds? It happened that there was. It's not infrared or ultraviolet. Neither infrared nor ultraviolet imaging can penetrate the dense, cloudy atmosphere to view and chart the surface with any sort of resolution. You require something else. Take a bow-dot radar imaging. Venera's Venus images have nothing on Magellan. In the 1970s, the Pioneer Venus Orbiter, also known as Pioneer Venus 1 or Pioneer 12, provided some radar mapping data, but its resolution was low and its images incomplete. Imagine trying to map the Earth, but Google Maps didn't let you zoom in further than 75 kilometers. New York City would only be a single pixel, so quite difficult to create an accurate map. Also, Pioneer 12 didn't chart the top and bottom tips of Venus. That's like a map of Earth with all of the Arctic and Antarctic circles cut out. The USSR started using radar to map the surface of Venus with their subsequent Venera models 15 and 16 in 1983. And made images with a resolution of 1 to 2 kilometers on the ground. NASA felt that they could do better. They wanted to see at all landforms, tectonics, impact and chemical processes, erosion, and even get to know Venus's interior. So they mounted an ambitious endeavor to image the whole surface of the planet in ultra-high resolution, and a gravitational map that would reveal what's below. That endeavor was Magellan. Now, before I reveal Magellan's images, you must grasp 3 important engineering breakthroughs that made Magellan's mission so revolutionary. First, to break through Venus's thick atmosphere, Magellan built upon Pioneer's rudimentary radar altimetry. Engineers employed a 3.7 high-gain Voyager antenna and the spare parts of other earlier missions to develop a synthetic aperture radar, SAR, that took multiple measurements of each region at various orbital positions. These multiple readings combined simulated the use of a much larger antenna, exposing unprecedented details of the surface. Second, Magellan took a polar orbital route, sweeping Venus in north-south strips with each of its 3-hour 15-minute orbits. Altogether, it ran 6 243-day mapping cycles. Cycles 1-3 mapped the planet's surface, and cycles 4-6 obtained gravitational field data. By May 15, 1991, when it finished its first cycle, Magellan surpassed its 70% mapping target, with a resolution of 83.7%. At the completion of Cycle 3, it had mapped 98% of Venus at a resolution of 100 to 250 meters. The probe actually returned more data than all of NASA's past planetary missions combined, a whopping 150 gigabytes. According to today's standards, it admittedly is not that big of a deal. Your phone most likely has greater storage space. But for the early 90s, it was something special. At last, after its third mapping cycle in September 1992, Magellan sent a steady radio signal to NASA's Deep Space Network. Using the way the probe's acceleration varied as it orbited around the planet, this would create a variation to the radio signal through the Doppler effect, enabling scientists to read Venus's gravity field. That told us about the interior structure and density distribution of the planet. The images I'm going to show you are 10 times sharper than any images that were taken with radar from Earth or from orbiting spacecraft before, and 250 times sharper than Pioneer 12's data. For the first time ever, we actually got to look at what was hiding behind those heavy, polluted clouds. Let us look. Where earlier missions had presented only blurry contours, Magellan showed us a world in exquisite detail, unveiling for the first time the surface features of our next-door neighbor. This mosaic took a decade to compile. The majority of the radar information from Magellan's readings. As you get close to Venus, you immediately see the absence of craters. In comparison to the Moon or Mars, it's quite unscathed, with Magellan only detecting 1940 impact craters on the whole planet. There are a lot of little impact craters missing, because their meteors burn up in the atmosphere of Venus. And the other craters we did locate didn't quite look like they should. Let's take these 3 craters, for instance, Danilova and Aglaonice. When it impacts, debris from the surface is thrown out and creates the pale yellow blanket-like formations around each crater. Crater ejecta deposit distinctive marks and shapes that enable scientists to ascertain the impact angle and energy and how long ago it occurred, the makeup of surface and subsurface materials, and much more. What's interesting about those crater ejecta is they all display sinuous flows in flower-shaped form, not unlike lava flows. They're composed of molten rock and stay in this form for far longer than expected because of Venus's hot surface temperatures. The Odivar crater is another good example of Venus's distinctive ejecta patterns. On airless planets, such as the Moon, material that is thrown out from an impact travels along an arced, ballistic trajectory. But on Venus, the debris that is thrown out interacts with the planet's thick atmosphere, producing high-speed winds that blow the material outward in low-altitude flows. This produces unusual streaks, such as the horseshoe-shaped one we're looking at here, and which occur only on Venus. And last but not least, the 90-kilometer diameter Adams crater has a 600-kilometer outflow tail, probably composed of impact melt or magma, which can remain in its liquid form for much longer due to the high temperature and pressure on Venus. The scarcity of these craters suggests Venus's surface is actually quite young. Indeed, gravity data collected by Magellan supports the hypothesis that Venus underwent a global resurfacing event approximately 300 to 500 million years ago. So what could have produced such a spectacular event?
Volcanoes, hundreds and hundreds of volcanoes.
We were aware that Venus had volcanic landscapes prior to Magellan, but we were unaware that an astonishing 85% of the world is blanketed with volcanic flows, such as these pancake domes, 65 kilometers in diameter with broad, flat summits less than a kilometer high. They probably developed from very viscous lava, which then cooled and retreated, causing the cracks and holes you can see in the photo. Or these vast lava flows, extending hundreds of kilometers across the broken plains beneath 2 large shield volcanoes, Sapas Mons and Maat Mons. By studying the varying shapes and patterns of these volcanic plains, scientists can identify different volcanic formation processes, from localized shield volcano eruptions to massive regional lava flooding events. Speaking of Maat Mons, let's take a closer look. Towering at a dizzying 8,000 meter tall, it's almost as large as Mount Everest. It's also a shield volcano characterized by its broad, gently sloping sides. They're typically formed by fluid lava flows like the Mauna Loa in Hawaii. Shield volcanoes are not the only kind of volcano you'll see on Venus. Small volcanic domes-like are also quite typical on the surface of the planet. As opposed to shield volcanoes, volcanic domes are created by small, bulbous amounts of lava too thick to travel very far. As it slowly emerges from the vent, the lava accumulates and hardens on the flanks. This cluster of volcanoes lies between coarse lava flows in the east and smooth flows of lava in the west, representing two distinct styles of lava overlying each other. Though the precise mechanism is still a mystery, the prevalence of lava flows and volcanic landmarks on Venus proved volcanism was the major factor in creating Venus's surface, and led to the theory that the world may still be volcanically active today. In 2024, scientists who were going back over Magellan's archival data discovered that 2 volcanoes indeed erupted while the probe kept watch. During the early 1990s, this backed up a historic discovery last year that Mons had erupted in 1991 too. So what is happening underground? What is Venus's mantle similar to? A clue to those answers is in the surface coronae, such as this 500-kilometer-wide Yavin corona. When heated, ascending magma from the interior of a planet's mantle reaches the surface or lithosphere. It makes its mark. On Earth, our tectonic plates move over this magma hotspot, forming volcanic chains such as Hawaii or flood basalts. But there is only a single tectonic plate on Venus, so mantle plume activity uplifts the surface before sinking as the magma cools. What's the result? These coronae, even though they're hundreds of millions of years old, many coronae are still well preserved. There are approximately 500 of them, spread out all over the planet in patterns that do not fit plate boundaries. And their style implies a lithosphere that is too thick or rigid to subside into mobile plates such as Earth's. All of this evidence points to a peculiar style of lithospheric deformation in which the crust remains mostly stationary but is shoved, pulled, and bent by forces beneath. This stagnant lid model planet may also play a role in Venus's runaway greenhouse effect. On Earth, our tectonic plates carry out vital processes like burying oceanic carbon. When it rains, atmospheric carbon interacts with mountain rocks to create new minerals which slowly make their way to the oceans, and eventually find themselves stored in seabed sediment. This sediment is then subducted when an oceanic plate submerges the seabed back into Earth's magma layer, a process that controls Earth's temperatures and carbon dioxide level in our atmosphere. As Venus's crust is motionless and lacking in tectonic activity, such a control process can't occur. Instead, heat accumulates in the interior, and greenhouse gases aren't removed from the environment. The hotter the interior gets, the more unstable the system, until the entire lithosphere is overturned in a global resurfacing event, and the cycle is repeated. We don't really know how recently the last resurfacing event occurred on Venus, but NASA's technical report after Magellan indicates it was about 300 million years ago. The other interesting manifestation of Venus's peculiar tectonics and mantle activity are the tesserae we can observe in the highland areas of the planet. They are characteristic geological features marked by very deformed ground with the appearance of tiles. They make up around 8% of Venus's surface and occur mostly in the highland areas. As some of the oldest surface features visible on Venus, they are approximately 750 million years old. The USSR's Venera 15 and 16 missions initially discovered these structures in the 80s, but Magellan brought them to life in dramatic detail, such as this image of Alpha Regio, one of most of Venus's most prominent tesserae. Scientists are still not certain precisely how tesserae are created, but the two leading hypotheses suggest they are probably composed of volcanic rocks, or they belong to Venus's continental crust bent by compression or expansion. If that's the case, they'd be portals into Venus's geological history, and perhaps even reveal to us what the climate was like a billion years ago. Amazingly, Magellan was actually able to record the first evidence of active tectonics occurring on another planet in the solar system in Venus's Aphrodite Terra, a region of continents about the size of Africa. The photo on the left was shot in late November of 1990 during Magellan's initial journey around Venus. The photo on the right was shot 8 months later, as the spacecraft passed over the area for the second time. Notice the bright flow-like region that appeared? It is most probably caused by a landslide, possibly triggered by a Venus quake. On October 13, 1994, following one of the greatest success stories of deep space missions ever, the probe descended for the last time into the planet's atmosphere that it had followed with such devotion during the past 4 years. As it descended towards the planet's surface, it kept sending data regarding Venus's upper atmosphere before being engulfed by heat and pressure. Future missions. So now we know so much about our closest planetary neighbor. What is left to learn from Venus in the future? The answer is a lot. Of late, by far the greatest news about Venus has been the observation, or maybe not, of the gas phosphine high up in the Venusian atmosphere. In 2020, James Clerk Maxwell Measurements Telescope detected trace levels of the gas. Phosphine is generated by a range of different methods, but one of them, and the one that got everyone terribly excited, is by microbes in an oxygen-poor environment. Life on one of the most unlikely infernal environments possible? What a result that would be! But then other studies came along and could not find any such phosphine again. And by 2022, the possibility of its being in the Venusian atmosphere had been ruled out by NASA. It would have seemed that the results of the original study were wrong. But then Professor Jane Greaves of the University of Cardiff went on record at a high-level gathering in 2023. The JCMT had discovered phosphine again, this time further deeper into the atmosphere of Venus. Perhaps one day, future missions will provide us with a definite answer to this quite intriguing question. There are plenty of other questions left to be answered too. Why, for example, were two planets, Venus and Earth, the same size, evolved so differently? Was there in fact liquid water on the surface once upon a time?
What is a more accurate picture of the chemical composition of both the Venusian atmosphere and the surface that might help answer these conundrums?
After decades of being relatively overlooked in favor of Earth orbit assignments and outer planetary probes, Venus has suddenly garnered interest once more. A number of missions are planned to be launched on Venus in the course of the next decade. NASA's future VERITAS and DAVINCI missions will hopefully venture out to provide answers to questions such as, did Venus ever have water? If so, would Venus have been habitable? What has the planet changed over time? Is Venus volcanically active today? And lots more questions. Now set to launch in 2028-2030, should they go ahead, they will revolutionize our knowledge of Venus all over again. DAVINCI Plus will observe Venusian clouds on 2 gravity-assist flybys and send a descent probe deep into Venus's atmosphere to better understand its gases, chemistry, and water history. Although not expected to live through the landing, the probe will gather useful data and photos on its 1-hour fall to the planet's burned surface. Meanwhile, the VERITAS spacecraft will orbit Venus, like MAVEN already orbiting Mars. During the 3 Earth years it spends orbiting our neighbor. Its task will be to look for signs of continued volcanism and tectonic activity by monitoring heat emanating from the surface and examining the composition of Venus's tesserae. All these results will hopefully tell us just how different, or alike, Venus and Earth are. Unfortunately, I'm not allowed to speak about these missions without that qualifier if they go ahead, since VERITAS and DAVINCI are both missions which will be scrubbed if NASA's suggested budget reductions pass. MAVEN is already near Mars, and yet it too might be shut down in order to save money. You can read all about those budget reductions here, along with my opinion on it. But for now, let's just cross our fingers that these illuminating missions are allowed to go ahead as planned. But even if they do not, the other nations of the world are stepping up. ESA, Russia, China, India, and even one private American venture, the Venus Lifefinder, all are planning missions with goals that point Venusward. With any fortune, one, more, or all of them will take us on a journey of grand discovery of our dearest star of morning and evening, revealing a treasure trove of information and answering a few of our incandescent questions regarding Venus. Well, there you have it. Examining Venus in a range of differing wavelengths has provided us with considerably more information than visible light would otherwise provide. We've been able to distinguish volcano and crater features through kilometers of opaque clouds, identify some of the chemical makeup of atmosphere and surface, and apply infrared imaging to render the invisible visible to us. All of these have provided us with valuable clues as to why the conditions there are so extreme, and perhaps just that there is the potential, however small, of mere microbial life on our nearest neighbor. What do you want to know about Venus? What is your favorite thing about it that impresses you the most? Let me know in the comments below. I'll catch you later next time. Thanks for watching.